This is the video for our paper, Where to Explore, Few-Shot Affordance Learning for Unseen Novel Categories of Articulated Objects. Manipulating articulated object is a fundamental task in robotics, yet it remains challenging due to the diversity of articulated objects in the real world. The significant variance in the object structure, 3D geometry, and articulation types across categories make previous manipulation models struggle to generalize to novel categories. While training them on large-scale datasets is an intuitive solution to equip models with generalized manipulation knowledge, conducting real-world interactions with diverse objects or acquiring 3D models encompassing potential categories can be prohibitively time-consuming and costly. Since encountering novel objects is inevitable in real-world applications, few-shot learning has emerged as a promising solution. However, previous few-shot learning works usually focus on instance-level exploration and adaptation, requiring test-time interactions on each novel object, which is inefficient and unsafe. Recognizing this limitation, we observe that despite different categories have distinct shapes, they often share similar local geometries essential for manipulation, such as graspable edges and pullable handles. This property is typically underutilized in previous few-shot learning works. To harnessing this commonality, we introduce Where2Explore, an affordance learning framework that performs cross-category few-shot learning. When faced with a novel category, our framework could identify local areas that differ from shapes in the training categories for efficient exploration while concurrently transferring affordance knowledge to similar parts of the objects. After the exploration, our model could directly generalize to unseen objects in this category without additional test-time interactions. Our system is built in several steps. Firstly, we require a representation that encapsulates diverse semantic and geometric information from known categories to form a supporting set, from which we could expand the learned knowledge to novel categories. The desired properties in our system are fulfilled by point-level affordance, which provides per-point manipulation priors with detailed semantic and geometric information on various objects. We build a module to predict the per-point affordance. Given a specific action on a point in a partial point cloud, the affordance module is required to predict whether the given action will result in a part motion. The model is supervised by the ground truth interactions on the training objects. In this way, the affordance module is equipped with semantic understanding of geometries in the training categories. Next, we propose to explicitly estimate the similarity between geometries from different categories with the learned geometries in the supporting set. We create a similarity module to predict the proposed similarity. The module is conditioned on action parameters because even geometrically similar areas can have distinct semantic meanings when the action is different. We divide the training categories into two parts, the affordance category and the similarity categories. While the interactions on the affordance category are used to supervise the affordance module, interactions on similarity categories are kept from updating the affordance module. Instead, we compare the affordance prediction on objects from similarity categories with the ground truth interaction results and use the accuracy of affordance prediction during training to supervise the learning of the similarity module. This cross-category learning manner forces the network to focus on local geometries shared across different categories, thus measuring the generalizable similarity between local geometries from different categories with the learned geometries. After the similarity linking the supporting set and different geometries are learned, we perform few-shot explorations of novel categories under the guidance of the similarity module. Thanks to the property that similarity is conditioned on specific actions, we could sample interactions in diverse directions and poses. Then, by choosing the action with the lowest similarity prediction, the model performs a short-term manipulation trajectory and observes the result. Both the affordance module and the similarity module will be updated by this interaction and be ready for the next prediction. This loop will break if the similarity on the instance reaches a bar or the interaction budget is reached. To demonstrate the ability of our framework to propose informative interactions for cross-category exploration, We intentionally train our model with only 3 training categories. Then, we perform few-shot learning on 11 novel categories using only 10 instances per category. Finally, we test our fine-tuned model on unseen instances in novel categories to demonstrate that our model learns the general semantic and geometric information. Quantitative results demonstrate our framework's capability to efficiently explore novel categories by exploiting geometric similarity. We also conduct few-shot affordance learning on representative categories separately to match the real-world scenario. The results show that our method achieves the best performance in most entries. Note that our framework outperforms others by a large margin in pulling task, since pulling action is more demanding in selecting informative geometries to interact with. Visualization shows that, while affordance fails to directly generalize to novel objects, the similarity module can still discover areas that contain uncertain yet important semantic information to interact with. Through a few similarity-guided interactions on the novel category, the affordance could capture the geometric information of novel objects. Note that although we choose the same novel object for visualization, the adapted manipulation affordance could directly generalize to other unseen objects in this category. Comparing the visualization of our proposed similarity with exploration strategies of where to act and Afford that focuses on instance-level few-shot learning. Our proposed similarity is more geometric aware, successfully discovering uncertain geometries across different categories. We also conduct real-world demonstration, where the model has never seen mugs, but is required to perform few-shot exploration on 4 mugs and then manipulate another unseen mug. Thank you for watching.